Given f of x equals the square root of the quantity y squared minus x squared, determine which regions on the coordinate plane below are in the domain of the given function. Because we have a square root function, we need to recognize that the radicand, or the expression under the square root, must be non-negative for the result to be real. This indicates that y squared minus x squared must be greater than or equal to 0. It can be challenging to solve inequalities with degree 2 terms, but notice on the left side we do have a difference of squares. Let's go ahead and factor the left. We have the quantity y plus x times the quantity y minus x greater than or equal to 0. Now there's several ways to go about solving this. Let's consider 3 cases. First, if the product on the left is equal to 0, the inequality would be satisfied, which indicates y plus x equals 0, or y minus x equals 0, and the inequality would be satisfied. And then we have or. They can both be positive or they can both be negative, which means y plus x is greater than 0 and y minus x is greater than 0, or they're both negative, meaning y plus x is less than 0 and y minus x is less than 0. Going back up to the top, for the first equation, let's subtract x on both sides, which gives us y equals negative x, or let's go ahead and add x to both sides, giving us y equals x. So all the points on these 2 lines would be in the domain of the given function. Let's go ahead and graph y equals negative x, which is a line with a vertical intercept of 0 and a slope of negative 1, which is this line here. All the points on this line would be when y plus x equals 0, and therefore the product would be 0, satisfying the inequality, or all the points on the line y equals x, which of course is this line here, where the vertical intercept is 0 and the slope is 1. So all the points on these 2 lines would be in the domain. And now let's go to the first compound inequality. To solve y plus x greater than 0, again, we'll go ahead and solve for y by subtracting x on both sides, giving us y greater than negative x, and let's go ahead and add x to both sides, giving us y greater than x. Because we have an and, we're looking for the region in which both of these inequalities are true. For y greater than negative x, we would shade above the line y equals negative x, which is this line here. So we'll go ahead and draw arrows in the direction we would shade, this region here. And y also must be greater than x. To graph this inequality, we would shade above the line y equals x, which is above this line here, and we shade in this direction. So again, we're looking for the region in which both of these inequalities are true, which you can see would be region A. Let's go ahead and shade region A. This region is in the domain of the given function. And now we need to solve the last compound inequality. On the left, we'll go ahead and subtract x on both sides. We have y less than negative x, and on the right, we'll add x to both sides, giving us y less than x. And again, we're looking for the region that satisfies both of these inequalities. To graph y less than negative x, we would shade below the line y equals negative x, which should be below this line here. And y is less than x, we would shade below the line y equals x, which should be below this line here. We're looking for the intersection of these 2 regions, which we can see is region C. To answer the question, which regions are in the domain of the given function, which we can see are regions A and C, but I also want to mention the boundaries are also included in the domain, meaning the lines y equals x and y equals negative x. Before we go, let's look at the graph of the given function. Here's the graph of the given function. Notice we have half of a double cone above the xy plane. If we look down on the xy plane, we can verify the domain. Notice region A and region C are the correct domain for the given function. I hope you found this helpful.